Hello, everyone, and welcome to our live session for today, September 24th, 2025. My name is Matthew. I am one of the course staff for our online courses. I run some of the behind the scenes operations for these live sessions. Welcome. We are excited to be with you here today. I'm just going to go through the sort of mechanics of how these live sessions work. Please post your questions in the chat. We will grab them from there. I generally try to go in order, but sometimes I jump around to try and give a variety of people an opportunity to have their questions answered and to get a variety of topics. We have this is an introductory level discussion. So if you have really advanced questions, we probably will not get to those during these live sessions. So keep those questions at an introductory level. Also, we do see all of the questions that come through the chat, so please ask them only once. Don't spam the chat with the same question over and over again, thinking that we will pick it. In fact, it makes me less likely to pick it if I see people are abusing the chat. I think that is it for today. For the announcements, make sure you hit that thumbs up button, like and subscribe to our channel because that helps us boost our reach for getting new viewers and new subscribers. If you want to get announcements about upcoming live sessions, also follow our YouTube channel or scroll to the top of the chat. There's a link where you can join our Google group listserv. There's also a Google Calendar invite, so you can add that to your Google Calendar and it will populate it with all of the scheduled live sessions. Chris, why don't you say hello to everyone? And if you have a topic for sort of stimulating discussion today, we can get started with that.
Sure. Welcome, everyone. I was going to talk today initially about a very nice result recently from the Event Horizon Telescope. The Event Horizon Telescope is a network of radio telescopes working at millimeter wavelengths that is able to take exceptionally sharp radio images of distant objects because it spans the entire face of the planet, and that by the rules of angular resolution means you're essentially getting the angular resolution of a telescope with the equivalent size of the Earth, although not the collecting area, obviously. We have one of the telescopes on Kitt Peak that's part of that array. I think there are almost 12 or 13 telescopes, now part of it, distributed around the planet. And the spectacular discovery a few years ago, which made front page headlines, was the image of the black hole in the center of the distant galaxy M87, active galaxy. It was a picture of the black hole silhouetted by the accretion disk. And then a few years later, they followed that up with an image of the black hole at the center of the Milky Way. It's been hard for them to find more examples of black holes they can image. However, they've been observing M87 for years now, 3 years, and they've started publishing the results of that monitoring. And essentially what they've seen is real variations in the near physics of the black hole, the accretion physics of the black hole, which is very exciting. And the tool they're using really is polarization. So because radio telescopes have a radio feed, which has a linear direction, they easily measure the polarization of the radio waves that are coming in. And in the world of physics, polarization easily relates to the magnetic field orientation if you're dealing with a magnetized plasma. And so in this case, they've made magnetic field maps of the accretion disk right from the first image a few years ago, and now they've observed the magnetic field changing over time. And so they've released a little animation and a movie and video of these changes, and they're quite impressive. And they've actually seen magnetic field reversals in parts of the accretion disk. It's hard to interpret some of this variation. It's exciting that it's happening, but it speaks to very detailed accretion physics. This is the black hole fueling through the accretion disk, and it's quite a complex, turbulent situation. But the fact that they can map it at all, that far away, 60 million light years, and at an incredibly small physical scale, is a remarkable testament to the power of this radio telescope or set of radio telescopes.
Excellent. Thank you very much. If any of you have questions related to that, put those in the chat and we can uh, discuss it further. The first question that we will take here today is from Saad, who's on with us live. And it says, "Hello, Professor. Why are stars distributed in arms around the centers of spiral galaxies rather than in rings, since that stars follow circular paths around the center of these galaxies?"
Right. It's a good question, and it's sort of asking why do spiral galaxies have spiral arms when the motions of the objects in the spiral arms, the stars and also the gas and dust clouds, are circular around the center of the galaxy. And that's because the spiral arms are actually a pattern. They're not a sort of fixed physical location. So it essentially is a compression wave, a sort of compression wave where as stars and gas pass through the compression wave on their circular orbits, they are compressed, and so that leads to more star formation in that compression. And then when they leave the wave where there's an increased density, that is relaxed, and so the star formation ceases. So essentially, the spiral arms are maps of increased density where the increased density is causing enhanced star formation, and then the stars continue on their circular orbits and leave that situation. So these are temporary, these are evanescent patterns. In other words, the objects that are in a spiral arm right now in the Milky Way are not the same stars and gas clouds that will be in the spiral arm billions of years from now. It took a while to figure this out, and it wasn't until the mid-20th century that people understood the nature of spiral arms in galaxies.
Excellent. Thank you. The next question is from Faisal, who's on with us live, and asks, "Why do we only talk about Betelgeuse going supernova when other visible stars also are or might be in their final stages?"
It's true, Betelgeuse is getting a lot of attention, and that's just because it's a very bright, well-studied star in the Orion Nebula, obviously in the Orion constellation. And it's a fairly close star for that luminosity. And so if it did go supernova, it would be a spectacular event, visible clearly on the Earth, probably brightening to a daytime visibility of the supernova, not threatening the Earth. It's not that close to cause radiation damage to the Earth. And yes, there are other massive stars that potentially could die as supernovae, but it's very hard to age date a star in its advanced phases of evolution and then pinpoint how far or how long it has to go before it detonates as a supernova. And none of the other massive stars that will die as supernovae are well dated or have very good measures of their exact state of evolution. Betelgeuse, the data is better because it's nearby, it's been studied for a long time, and it's clearly unstable at the moment, and that is often a precursor to the final destruction as a supernova. So it's getting attention, extra attention because of that, because of its proximity, because of its brightness, because of the instability that could precede the supernova event, but still does not allow us to predict it with any kind of accuracy of even at the level of decades or centuries.
Thank you very much. The next question is from Birhane, who asks, "How would quantum physics and quantum computers help in developing more powerful telescopes?"
Well, quantum physics is involved in astronomy detectors because many of the detectors that astronomers use, from not just at optical wavelengths with a CCD, but at radio wavelengths and millimeter wavelengths, involve quantum physics. Getting the detector to work requires phenomena that operate at a quantum scale, and sometimes they're very specific to quantum effects. So detectors definitely use quantum physics. Quantum computing, if it ever emerged from the laboratory or the research arena, would of course transform astronomy, because we are dealing in astronomy with huge data sets, a sort of deluge, a fire hose of data from big surveys such as with the Rubin Observatory that started taking data, and with other space-based observatories, Hubble and James Webb. So reducing data like that is taxing the computational capacity of current supercomputers. And so quantum computing would absolutely affect astronomy. It would impact every scientific field. High energy physics generates huge amounts of data too, say at the CERN collider. So I think quantum computing will be a powerful tool across fields of science.
The next question is from Natalie Walker, who is on with us live. Are the spectral analysis methods we use in astronomy similar to those in chemistry labs? Do spacecraft instruments directly analyze samples, or do they rely mainly on light emitted or absorbed by the target?
Yeah, the power of spectroscopy is similarly experienced in a chemistry lab and in an astrophysical experiment. I mean, basically, uh, it is common to, disperse the light from a sample that's either emitting or absorbing light into a spectrum and then see what the sample is made of. Now, in the lab and in chemistry situations, the luxury you have is you have as much light as you can. You can use an enormous amount of light in that situation, so you're not starved for light. In astronomy, you're often starved for light. So when you make a spectrum, you're taking possibly an already very faint, very distant source and spreading its light out across wavelengths. But the tool is essentially the same. Spectroscopy is a way of determining what something is made of chemically because of the sharp spectral transitions that are unique to each element.
Sorry about that. I clicked the wrong button. The next question is from one of our live participants, Ayush. Would like to know, for researching in modern astronomy, should I or should a potential student focus on learning computer simulations or learning data analysis of telescopic data?
Well, they're both important. I guess overall, in terms of the research field of astronomy, the fraction of researchers that are simulators, if you like, that are using high powered computer simulations of various phenomena, that's a lot smaller community than the community of observational astronomers who are using computers for data reduction. So in terms of, hitting the talent or the skill that most astronomers use, because most astronomers are observers, then observational data reduction would be important there. It's also worth noting that to be a simulator, to be an astrophysics simulator in this field, is quite a high level of technical skill. It's not that you're just using powerful computers or even just programming them. You also have to know in great detail how different algorithms work and what the limits of computing are. Because if you don't get that right, then what comes out of a simulation is essentially wrong. So it's a science and it's also an art. And there's only a few hundred people who are really good at that kind of work worldwide.
The next question is again from one of our live participants. Anjali would like to know, how can we tell the difference between ether and dark matter?
So ether is a term that goes back to the Greeks, the ancient Greeks. And they speculated or wondered whether the universe beyond the earth was filled with an evanescent substance, an invisible, translucent perhaps substance that was not terrestrial. So it wasn't, they had the four elements: earth, air, fire, and water. And then the ether was sort of a fifth element, sometimes also called quintessence, meaning it is the fifth element. And so that was the conceptual origin of the ether, the idea that space wouldn't be truly empty, because that was hard to imagine, the vacuum of space and possibly infinite space. And so the ether idea came that way. The ether as an idea continued through the 19th and into the 20th century, when people wondered what it was that allowed light to travel through a vacuum as an electromagnetic wave. What was the medium through which this wave was propagating? Because other waves we're familiar with, like sound waves, have to propagate through a medium. So they postulated that there was an ether to essentially be the medium through which light and electromagnetic waves propagate. But experiments in the early 20th century, the Michelson-Morley experiment and a few others, definitively showed there is no ether. There's no medium that's carrying light. Light travels at 300,000 kilometers per second, regardless of the source and the motion of the source and position and situation in the universe. It's a profound result, and it was the initiation of the special theory of relativity. So the idea of the ether has gone away, and it isn't formally or even indirectly related to dark matter or dark energy. These seem to be different substances that we will have to understand with different types of observation.
Excellent, thank you. The next question is from an email. Wendy sent in this question. What do you think of um, theories about the universe, such as like anti-universe theories that suggest symmetries where time would flow backwards that would eliminate the need for inflation and dark energy?
Well, people are worrying about proving or getting better evidence that inflation occurred and also trying to understand what dark energy is at all, because we really have very little idea. These exotic universe theories you're asking about, anti-universes where time flows backwards, completely hypothetical and speculative. There's no evidence that such a universe could exist or does exist or has existed. And also our current laws of physics that we put a lot of faith in because we've tested them not on only on Earth but beyond the Earth, do not really predict or explain such a universe. So we'd be looking for new physics too, and nobody knows what that new physics would look like. So I think these ideas are pretty much stuck in the realm of speculation at the moment.
The next question is from Jim, who's on with us live, who asks, is quantum gravity the missing link in the standard model?
Well, quantum gravity is definitely a missing link in physics because we don't have a way to reconcile general relativity, our theory of gravity, and quantum mechanics, our theory of how microscopic particles, waves, and fields work. And that's a big omission. These two theories, each of which is excellent and well tested in its own realm, they're immiscible fluids. They don't mix well, they don't combine well, the mathematics is different. And so quantum gravity is a one way to try and resolve these issues by somehow deriving gravity in a way that's quantized. And that's very different from general relativity. General relativity postulates that space-time is, in mathematical terms, a manifold, and that is a smooth space-time with no discontinuities, no disruptions, no ruptures, no folds, no creases, no holes. So it's fundamental to general relativity that space-time is smooth and continuous, even though it can have curvature. Quantized space-time would be something totally different. So quantum gravity is a fundamentally different type of theory. And people have made efforts at coming up with such a theory really for a few decades now. And none of these speculative theories is yet viable, nor does it make predictions that can be confirmed.
The next question is from Lawrence K., who has a question regarding quantum decoherence. Does a quantum system lose or gain energy in transition to a classical system, and how does this transition operate?
Well, when quantum entanglement is induced in a quantum system, that is a coherent state, of course, of energy, because the energy states of two disparate particles, subatomic states, are connected. The system as a whole is still subject to the laws of physics, so the conservation of energy and so on. And so when you decohere such a system, each of the entities, particles typically involved, will resort or relax to its original energy state. So when they're entangled, their energy state is different than those of the individual particles before they were entangled.
The next question is from Hernan Reyes, who sent an email. Hernan has been reading about Lake Vostok, the enormous subglacial lake in Antarctica. And his question is about the development of life in that kind of sort of isolated system. There is some evidence that there are thermophiles or streamophiles that are living there. Is it possible for life to have evolved in 25 million years in this kind of an environment on its own when archaic forms of life on Earth that we already know about took billions of years to develop?
So it's an interesting question. So just to give us a little more overview on Lake Vostok, it is a subterranean. It was discovered by radar imaging, essentially showing that there was a body of liquid water deep under the ice pack in Antarctica in a very isolated region. It's a substantial sized lake, but Antarctica is huge. so it's a small fraction of the Antarctic size, and it's many kilometers underground, and it appears to have been isolated from the surface and the rest of the biosphere for a very long time, possibly 20 to 25 million years. And so it's been the object of study, and it's been the object of controversy because the Russians in particular were drilling a deep hole. They were trying to penetrate through to the liquid layer through the ice, which is a hard job. It's a lot of drilling. It's almost at the limit of what we can do through ice. And there was a school of thought that said that they shouldn't do it. They shouldn't break through for two reasons. I mean, first, if it was a pristine ecosystem unconnected to the biosphere on top of the Earth, you would risk contaminating it immediately with the stuff that came in the drill bit or objects you introduced in the water that you flushed down under pressure to create the drilling situation. And then you could compromise potentially any living creatures that were in there. So it's indirect evidence that there might be extremophiles in this body of water. And then the question of where did they come from is, of course, fascinating. It didn't take billions of years for life to evolve on Earth. It's quite likely that it was present 3.8 billion years ago. That's just over 500 million years after the Earth formed. And there's indirect evidence it could be even earlier. So you don't need billions of years, but you do need hundreds of millions of years. And 25 million years may not be long enough. However, these are not static situations. A subterranean body of water under deep ice in Antarctica now may have been at a different location. It may have been connected to other regions within the ice or to the deep ocean over a long period of time, because the ice in Antarctic is not static. It moves, it shifts. It's not fully liquid, of course, but it's plastic enough to move, especially over time scales of tens of millions of years. So Lake Vostok has been isolated, we think, for that period of time, but in the previous period of time, it may have been connected to other regions and so not isolated. So if you find extremophiles there, you don't actually know that they had to have got their start in terms of going from inert matter to biology in 25 million years. They could have had much longer to do it. So there's huge uncertainties that lie across this research. But of course, the most important question is, can we safely and without forward or backward contamination explore this underground body of water and learn what life it contains? Because it is indeed very analogous to Europa, the watery moon of Jupiter.
Yeah, that brings us nicely to this follow-up question, which is why is the JUICE mission targeting Ganymede instead of Europa? Isn't Europa more likely to harbor some sort of life than its fellow Galilean moon?
So the JUICE mission, which is from European Space Agency mission, has some NASA collaboration and a lot of international participation, is a very ambitious mission to explore the watery moons of Jupiter. I think it's planning to get there around 2030, 2031 and start sending back data. So it's a long-range mission because it's going over 1 billion miles. The targeting of, in this case, 3 moons, Europa, Callisto, and Ganymede, was deliberate, and that's because they didn't want to put all their eggs in the Europa basket. But Europa is indeed a very promising world to look for life. But opinions have varied, and the limited data we have has varied as to whether the chemistry of these sub-ice oceans on Europa are actually admissible to life. It's not clear how hospitable to life the European Ocean is. The things of, the idea of the salinity and the pH and the chemistry of that body of water, all measured indirectly, of course, have varied. So it may indeed be a good place for life, and it may not be. However, Callisto and Ganymede in particular have also subsurface oceans. And Ganymede is the largest moon in the solar system, and it's about the size of Mercury almost, so it's the size of a planet. And it's indirectly measured, of course, because Callisto and Ganymede have a rocky, icy exterior, and the liquid water is under pressure with some geological heating from inside. As opposed to Europa, which is an ice pack overlying an ocean and then a rocky core. So there is a lot of internal heating from Ganymede because of its mass, and then the pressure from the rock ice cap keeps that liquid. And it's almost certain there is substantial ocean of water under Ganymede. So exploring Ganymede is a high priority. So these icy and watery worlds in the outer solar system, we know so little about them that it sort of made sense for JUICE to spread its bets and study three objects instead of just Europa.
The next question is from Terrence, who's on with us live. Professor, is it true that the asteroid belt was created or developed by a failed planet?
That's still the current view of the asteroid belt. The asteroid belt is in a zone or distance from the sun where you might naturally expect a planet, given the spacing of the interior planets and then the outer planets, which follow a roughly geometric spacing, but not exactly. So, based on that geometric spacing, the asteroid belt is where a planet might have been expected. If you swept up all the mass of the asteroids, squashed it into an object, I think it's 4 or 5% of the Earth mass. So it's not a very impressive planet if that's a failed planet. And the supposition would have to be that over 4.5 billion years, the debris in that zone or that region from the sun has mostly dissipated or scattered away by collisions and by solar radiation pressure and so on, such that only a small fraction of the material that was originally there remains in small rocky objects, and that's what we see as the asteroid belt. But yes, it is still plausibly called a failed planet.
The next question is from Sebastian, who would like to know, well, so the specific question is, why are we only sending signals every few minutes to aliens? But the more general question is, how often do we send signals? SETI type signals, where we would try to communicate with other intelligent creatures.
So we actually don't send signals very often or at all. So the experiment we're talking about is called METI, Messaging Extraterrestrial Intelligence. So it's a counterpart of SETI, which is the search, which involves the listening experiment. And the transmitting experiment is controversial. So it's just fair to say that up front. Because some people, as esteemed as Stephen Hawking before he died, said we shouldn't do this. We shouldn't transmit information about the Earth and its existence and the fact that we exist as a technological civilization. Because if that message were received and the aliens had a malintention, then that could be really bad for us. And that's a fair perspective. So to be on the precautionary principle, you'd actually just stay quiet and you wouldn't transmit at all. But there have been some METI experiments, but I'd say only a handful. In the last few years, just a handful. And overall, maybe about a dozen. So it's far fewer than the number of SETI experiments. And often the targets of these messaging experiments, starting with the one in 1979 from the Arecibo dish, which went, I think, to M13, which is a globular cluster 65,000 light years away. Obviously, sending a message 65,000 light years means nobody's going to come after us and get to the Earth, even at light speed, for 130,000 years. So there's no practical danger there. And indeed, many of the targets of these initial messaging attempts are quite distant stars, so there's no proximate danger. That's the reassuring way to put it.
The next question is from Ratkas, who's on with us live and asks, what is the best life lesson that you received from either parents or professional life? Can you think of a life lesson that you received that was valuable and that is worth passing on?
I mean, that's an interesting question. I had a number of life lessons when I was young. My family moved around a lot. I went to 10 different schools, I think, before I graduated to college. So I think one of the life lessons I learned is that, change happens and turmoil happens and turbulence happens in families and dislocation and so on. I'm not comparing my level of dislocation to some other families. That you just put your head down and persevere and study, I mean, school is important, learning is important. So I got that message just very strongly from my parents, supportive of my learning and studying and taking school seriously. And that's always a powerful message for parents to give their kids.
Short Educational Videos, who's on with us live, asks, what do you think is the single biggest unsolved problem in aerospace engineering today? So like space travel and, aerospace kinds of um, problems?
I mean, if I were to just, I would give different. There are possible answers to this. Depends on the time frame, but in terms of the long future of space, it's not particularly an aerospace engineering problem. It's almost a biomedical problem. I would say the biggest unsolved problem is suspended animation or hibernation, because if humans are ever going to leave the solar system, ever, the distances are so large that we cannot survive the journey. It's many lifetimes of a journey. And so, for space travel in that visionary realm of beyond the solar system, we need a technology that can take us down to a wait state or suspended animation, whatever, however you want to call it. And some primitive technologies like that exist. They've been used on animals, and have resuscitated pigs and dogs that have died after hours or weeks even. But these are far from the kind of technology you need to be able to go to the stars. So that's a particular kind of aerospace problem that relates to the vision of leaving the solar system.
The next question is from one of our live participants. Can you elaborate on the tidal forces of Enceladus? Is there actually heat generating from its core?
Yes, the tidal force exerted on Enceladus is a function of its elliptical orbit. It's not in a circular orbit of Saturn. And so it experiences a strong gravity force, of course, from Saturn because it's orbiting Saturn. But any object like a small moon, and it is a small moon of a giant planet, and Saturn is a giant planet, will feel a differential force that changes as the distance from the object changes. And so because it's an elliptical orbit, it will experience a squeezing force as it moves around its orbit. It's fairly gentle, but it's repeated every time in the orbit, every time it moves around its elliptical path. And so that heating force operating over many orbits and millions of years is a substantial heating effect on an otherwise small moon, because Enceladus has too low mass for geological radioactive heating from its rocky material to provide significant heat. So I think in the case of Enceladus, the tidal heating is the largest heat source in that little moon.
The next question is from Monty, who's on with us live. With current technology and the possibilities of near-term solutions, when do you think humans can go to Mars, if ever?
It's going to happen, I think, but not quite on the time frames people are talking about. It's a tough journey. It's essentially it's a 2-year journey. There are launch windows that you have to wait for roughly every 26 months when given the different orbital speeds of the Earth and Mars, when you have a minimum energy orbit or trajectory to get from the Earth to Mars. It's called a Hohmann orbit in the technical speaking about space trajectories. So there are windows or minimum energy for transmitting a spacecraft and humans to Mars. You have to wait for that. And then the journey itself on that minimum energy path will take 7 or 8 months. And then you have to wait for the next orbital window to return. So the entire Mars mission will probably imply 2 to 2.5 years and some amount of time on the surface, 4 to 6 months. And the ability to do that and sustain humans for that is quite prodigious. Think of what it would require for a minimum crew of, say, 3 people. How much food they would require for 2 years, because there's nothing on Mars. You have to bring everything with you. Eventually, maybe we can have a base and grow things and so on, but not the first time. So that's part of it's that sort of the length of the mission, because it's far away, and the fact that you have to bring everything with you, all your supplies, all your materials, means there's a lot of energy required. The Starship, Elon Musk's giant rocket, is of course designed to do that. That was why he had the vision of the Starship. But the Starship is really very far from getting there. Remember, the Starship has not made it into full Earth orbit yet in 9 test flights, I think. And then it hasn't gone beyond the Earth. So for Mars travel with Starship, you'd have to demonstrate refueling in orbit. That's, of course, another difficult step. And then you'd also have to be able to show how Starship could land and then take off again from a foreign world, from Mars. Starship operates off a launch pad with a lot of infrastructure in Texas. So on Mars, none of that exists again. And so the act of landing and then taking off again safely from Mars, which you would need to return those first visitors to Mars, is completely unproven and obviously very hazardous. So there are huge technical issues and undemonstrated steps in the path to getting humans to Mars that SpaceX will need to do, and of course NASA would need to do, or the Chinese Space Agency, because America and China are both planning at some point to send humans to Mars. And the timeline for them, the governments involved, is a couple of decades.
The next question is from David Gold, who's on with us live. Why does astronomy choose a phase of the moon that is not visible to naked eye as the new moon, rather than the first sighting of a lunar crescent, as some religions have done for millennia?
Right. So, I mean, it's a good point to refer it to religion and say that the Islamic countries that use direct observation of the moon to set their calendar, and they follow a lunar calendar. So, unlike the sort of Judeo-Christian traditions, which eventually originating with sun worship, thousands of years ago, used a solar calendar. Islamic religions use a lunar calendar. It's based on direct observation of the crescent moon just after the new moon phase. Astronomers really need to be more accurate than that, because if you're just relying on when you actually first see the crescent, that's got a modulation period of a day because you can't see the moon for some fraction of that 24-hour period. So it's not on its own a very precise sighting of the first crescent. You just see it when it's just above the horizon and visible to you, not blinded out by the sun or by daylight. Astronomers can calculate the new moon much more accurately because they know what the orbit is. And so even if the new moon is not completely visible because that there's essentially no reflected light coming to the Earth, astronomers can calculate it accurately. So for astronomers, it's a much more sensible way to calculate time and keep track of the lunar cycles.
The next question is from an email. Doug Nicole sent an question about the recent discovery of the galaxy MOM Z14. That's a very young, well, its age of only 280 million years after the Big Bang. Does that change the current cosmological understanding about the age of the universe? And if so, how?
No, this is an exciting discovery. This galaxy, about a quarter of a billion years after the Big Bang. That's very soon after the Big Bang, of course. That's looking at a redshift and a time when the universe was almost an order of magnitude smaller and hotter and 3 orders of magnitude denser than it is now. So quite a different universe. It doesn't break cosmology or violate anything we know about galaxy formation, because there's a selection principle operating here. When we look for distant galaxies and look for the most distant galaxies, we're always going to find the most luminous and most obvious object at any given distance, because those are the ones we can detect. So the ones we detect at any particular distance are not necessarily typical. They are particularly luminous. Now in this case, them being luminous and potentially massive makes a bigger problem for cosmology, because how did you grow such a big luminous thing so quickly? But it also means the conditions in that galaxy or the way that it formed its stars may be unusual. Perhaps it suffered interactions with another primeval galaxy and got compression waves that formed a lot of stars very quickly. You don't know the special circumstances. So you're sampling things that are unusual from a population. And it's really not until you study the whole population or a larger number of objects at that redshift that you can draw some conclusion about cosmology. So for the moment, it remains a very interesting object, but it's not indicative of any big problem in cosmology.
So kind of a follow-up question to this is, might we just see more and more galaxies as we're able to look deeper into?
Well, that's been happening. So James Webb is pushing the boundary of what we know about the distant universe. It's finding higher and higher redshift galaxies. It's why James Webb was designed more as an infrared telescope than an optical telescope like Hubble, because Hubble Space Telescope essentially can't look at very high redshift objects. Their light has been redshifted beyond the visible range. So James Webb is doing the job it was designed for. Will it run out of steam? Will it see what people in astronomy call first light? That was the hope. That sort of was the killer app of the James Webb Space Telescope. So we haven't got there yet. I think there's still room for galaxies to be formed even earlier, perhaps as little as 100 million years after the Big Bang. And James Webb should just be able to see anything that formed that early. But that's about the limit, even for James Webb.
The next question is from Yang, who asks, are there any promising theories to explain the cosmological constant?
Well, the cosmological constant is the relic from Einstein's theory where he solved the equations of general relativity, and because at the time in the 1910s and before the discovery of the expanding universe, before Hubble's work, the universe was thought to be static, and so general relativity produces dynamic solutions of space-time, either expansion or contraction, and to force general relativity, the solution, to be static, he had to add the cosmological constant. So it's an integration constant in one of the solutions of the equation. And so it's an artifact essentially of a theory where you're trying to create a static situation from a theory that's fundamentally dynamic. And it has the attributes in terms of the math and the dimensionality of dark energy. And so people have associated the cosmological constant with dark energy, and in the framing from general relativity, the constant would be constant over space and over all time, and that's what we're seeing about dark energy. So there's the connection between the two conceptually is significant, but their origination in theory is really quite different, and we don't have a good theory for dark energy, so that part of the equation is completely missing.
Excellent. We have two sort of LIGO related questions. Kevin, who's on with us live, asks, I want to know about neutron star collisions. What is their likelihood? What sort of waves and signals do they produce? And what are the end results of these collisions?
So LIGO has been successful, has really been successful. It's sort of like a factory now for generating results of black hole collisions. They give the strongest signals because those are most collapsed objects. Also black hole neutron star collisions, and then neutron star collisions, which are weaker signals because neutron stars are not as dense, so their space-time ripples are not as strong. But there are neutron star collisions that are being found, and the simulations in theory of what those neutron star collisions do are fascinating. And some of the theory preceded LIGO's first detection, so this is almost a prediction of what LIGO would see. In the computer simulations, the enormity of the energy involved in a neutron star collision will force neutrons into atomic nuclei and vault them up the periodic table. And so you can create all the heavy elements with a neutron star collision. And then the detonation of that, the release of that material and the energy involved is where a lot of heavy elements come from. So rewriting the book on cosmic chemistry about 10 years ago, we learned that probably more than half of the gold, platinum, and silver, sort of precious elements, that type of heavy element, is produced in neutron star collisions and ejected into space. Most of the rest of it comes from supernovae. And in fact, in one neutron star collision, a prodigious event from 2017, it was estimated that two neutron stars, colliding, generated about 13 Earth masses of heavy elements that were ejected off into space. So, fantastic amount of heavy elements. Heavy elements are rare. There's only one gold atom per billion hydrogen atoms in the universe. So, heavy elements are rare, but they're produced in enormous quantities by neutron star collisions, which are themselves rare because neutron stars only are left behind by massive stars when they die, and the odds of two of those massive stars being in an orbit where the neutron stars eventually will collide is very low. And so neutron star collisions, we think, happen once every 100 million years or so.
The next question is from Dave McKenzie, who sent an email. How do astronomers determine if a gravity wave was generated by colliding black holes or from other sources?
So it's quite a sophisticated business now, interpreting gravity waves. And the theory and the simulations were done before LIGO was constructed. In fact, you couldn't have really justified the incredible amount of money and the precision of this unprecedented physics experiment unless you had pretty good confidence you were going to detect something interesting. And so theorists had been using computers and then pure theory also to predict what the signature of black hole collisions and neutron star collisions would be. And they have a very particular waveform, because there's a slow in spiral where there's release of some gravitational waves, and then there's a rapid in spiral and eventual merger, and then what's called a ring down phase where the combined black hole or combined neutron star oscillates as it settles into a final state. Each of those phases has a quite particular signature of gravitational waves. Obviously, the most intense gravity waves come from the coalescence, from the merger itself, the final in spiral and merger. But those signatures were well known and predicted before LIGO ever took any data. So when LIGO started making measurements, you're essentially using your theoretical prediction and your simulations as a filter to look in the noise, because most of what LIGO detects is just noise, geological noise, thermal noise, electronic detector noise, and filter out this particular crescendo signal. And that filtering with a matched filter of what you would expect theoretically worked extremely well. And that's how LIGO is really able to detect these events. Now, it has a little downside. There's a downside, as you can imagine, which is you only detect what you're looking for. So if there is other physics or other different types of signatures that we don't know how to anticipate or how to model, then our detection techniques probably won't find them. So we find the things that we predict to be out there and we expect and that have the behavior we anticipate, given our good knowledge of the theory of gravity. But that doesn't mean we found everything that there is to find with an instrument like LIGO.
Excellent, thank you. The next question is from Gabrielis, who asks, do you have any examples of events in science where there wasn't an understanding of uncertainty and error, um, as you talk about in one of the course videos? So, that where because we didn't understand uncertainty and error, it gave us a bad prediction or bad information,
Mm.
or the measurement was somehow incorrect.
So the best examples of this are involve systematic error. So in science and in astronomy in particular, there are usually two kinds of error. There's sort of random statistical error just due to sampling or due to noise in your detector. So it's random in nature and it'll have sort of Poisson statistics. And that error is pretty easy to understand. And you drive down that error by taking repeated observations and independent observations with different facilities. And it's well known how to handle that error. Systematic error is something different. Systematic error is a skew in what's going on in the object you're observing that lets you misinterpret it. And it also means your physical understanding may have been flawed that leads you to misinterpret what you're seeing. And astronomy has a number of these examples. Sometimes they involve the fact that we don't understand the physics of something. So, for example, it turns out there are two types of Cepheid variables. Cepheid variables were, of course, pivotal in used by Hubble to measure distances to galaxies based on their period luminosity relation. But if there are different types of Cepheids with different oscillation physics, then your period luminosity relationship is going to give you the wrong answer. So that's a kind of systematic error where you're just unaware of some important physics that leads you to calculate or infer something that ends up being wrong. And the trouble is the data itself is not going to tell you that. So gathering more data will not get rid of a systematic error. That's the fundamental difference. And astronomy, that's just one example, has been subject to systematic errors over hundreds of years since we've been taking data. And with the universe, where you can't study it in the lab and you can't alter parameters at will, that's a really fundamental issue in astronomy.
Excellent. Thank you very much. So the next question is from one of our live participants, and I think the question itself has kind of a fundamental misunderstanding. So I'll read the question, but then we can clarify what that is. So when observing the microwave background radiation and those sort of what look like heat map images, are those plasma clouds at the edge of the universe?
Well, the microwave background radiation is it is a plasma. It's actually looking back in time to 400,000 years after the Big Bang, when the universe went from being a plasma to being a neutral gas. In other words, the microwave background radiation corresponds to when the universe became transparent because electrons attached to protons making neutral stable hydrogen, and light could travel freely. And that light, originally light back then, stretched in wavelength by billions of years of travel through expanding space-time, becomes microwaves as we observe it. It is actually a plasma. You're looking at the transition from plasma to a neutral gas, and it's as far as you can see back into the universe, because a light does not travel through a plasma, and so there's no radiation information from earlier in the history of the universe than about 400,000 years after the Big Bang.
Excellent. Thank you very much. The next question is from Arif Roni. Before Stephen Hawking's ideas about black hole radiation, scientists didn't think that black holes could give off radiation. Can you talk a little bit about the quantum phenomenon of this Hawking radiation?
Right. So black holes are black in classical black hole physics. Black holes, of course, were found because they turned out to be very bright objects. Because when black holes are gathering gas and are surrounded by an accretion disk or being fueled by an interaction with another star, that gas gets very hot and emits a lot of radiation and accelerates particles and so on. So ironically, although black holes are black, the brightness of them as observational entities is because of their interactions and their fueling. Hawking radiation is something different. That says that black holes emit radiation intrinsically because of a quantum phenomena that occurs at the event horizon, where particle-antiparticle pairs, which are always coming in and out of existence in the vacuum of space, one member of a particle-antiparticle pair goes into the black hole and the other escapes, and so the net effect is radiation. If the antiparticle escapes, it will meet matter and create photons, so that's radiation. And if the matter escapes, then that will lose a small amount of mass from the black hole, and so the black hole evaporates. So quantum Hawking radiation and black hole evaporation are intrinsically linked. They're essentially the same physical phenomena. It's important to emphasize that this is a prediction of Hawking from the 70s that has not been confirmed. We've never observed Hawking radiation. We've never observed any black hole evaporating because the radiation is so subtle and so low temperature, and the evaporation rate is so slow on a human lifetime scale that it's essentially unobservable.
The next question is from Dan Cooper, who is on with us live. Do you know how far along the Chinese are in developing the technology to build solar panels in space that would transmit electricity back to Earth through microwaves? I know Caltech is also working on this. How far are we from being able to capture solar power in space and beam it back to Earth?
Yeah, so the Chinese interest in this is important. China is very advanced in their use of solar power. We know that because in the United States, solar panels are almost all made in China, and worldwide that's the case. And China has an enormous amount of solar power at the moment. It may be that they think they can solve their energy problem with their population of 1.5 billion people getting richer and using more energy simply by renewable energy sources available to them, and they're still using fossil fuel too. But for their space ambitions, they realize they need energy in space, and it's not necessarily just to capture energy in space and beam it down to the Earth, although that's a long-term goal. But in the short term, it's for distributing energy and relaying it to places where they might want to visit, such as the Moon and Mars. So the Chinese have pretty big ambitions to go. They've been to the moon, of course. They have ambitions to go to Mars, perhaps to return samples from Mars before the Mars sample return of NASA will actually bring back samples, and then to eventually set up a moon and a Mars base. And in that situation, having a solar collection facility in Earth orbit and ability to beam it as microwaves to a distant location is very powerful. It could essentially solve the energy problem, particularly on the moon. Mars is much more difficult because it's so far away. So I do think the Chinese have plans for capturing solar radiation and having solar panels in orbit to serve, also potentially serve their energy needs of their own Earth orbiting hardware, but also for the ambitions of moving beyond the Earth.
The next question is from Anjali, who's one of our live participants. Is Antarctica available for tourism?
There are tours of Antarctica all the time. So the research stations on Antarctica, which are owned in different locations by 8 or 9 different countries that have claim to Antarctica or science interest there, those are not typically open for tourism. There's a layer of what I'd call scientific tourism, where people who are scientists or government officials or diplomats or dignitaries are able to go there and visit. And it's essentially tourism because they're not doing the work at all. But tourism in Antarctica is a big deal. There are cruise ships that go to Antarctica, certainly not in the austral winter, but throughout the austral spring, fall, and summer routinely. And they mostly will not land. Mostly they're just sea voyages where you get close and see things but don't actually land. But some of them will land on the Ross ice pack typically. And then there are some tourists that get to go to McMurdo Station, the U.S. Antarctic Research Station, because it has finite capacity, a small capacity for visitors, paying tourists basically. So yeah, tourism in Antarctica is quite a big thing now, and it's quite lucrative for the companies that do it because they can charge obviously quite a lot of money because it's a very special bucket list type location for most people.
Excellent, thank you. It is 10:59, so we are going to wrap up. We'll take one final question for today, and then that'll be it, and we'll be back again in a couple of weeks. The next question is from one of our live participants who asks, what are your thoughts on Mars moon Phobos and it not having a bright future as it moves closer to the planet by 2 centimeters each year, which seems small, but it seems like will it eventually crash into Mars? If so, when could that happen and what would that be like?
Yes, so Phobos, it's true, it is approaching Mars by a very small amount, 2 centimeters a year. That's actually twice as small as the distance by which the moon is receding from the Earth due to tidal interactions. Will it collide with Mars? Yes, but a very long time. And that's because Mars has such a tenuous atmosphere. Normally, if a moon starts to degrade in its orbit and approach a planet, as it enters the atmosphere, then drag with the gas of the atmosphere will greatly accelerate that process and lead it to, quite dramatically spiral in and crash. The Mars atmosphere is so tenuous, 1% of the atmospheric pressure of Earth's atmosphere, that drag process is very slow and inefficient. So I haven't seen a good estimate for how long it is that Phobos will orbit. It has suffered decay in its orbit before it crashes into Mars, but I'm going to guess it's 100 million years or more. Thanks for that question and the usual good range and some provocative and intriguing questions this week. Thanks to Matthew for facilitating, and I think we have maybe the next 2 sessions lined up.
Yes, absolutely. So I don't remember the exact date for the next live session. I'm looking it up right now, but it's going to be in 2 weeks. And that date is it's Monday, the 6th of October. So we move these around periodically to avoid trips and also to give other people a chance to join us. So the next session will be same time, same YouTube channel, and it'll be on Monday the 6th. And if you would like to hear about those sessions, make sure you follow our YouTube channel. And if you're still around, click that thumbs up icon so we can um, get the word out about these live sessions. Hit the bell so that you get an alert when you when we have another live session, and make sure you subscribe to our YouTube channel. So I think that's it for today. Thank you all for the fantastic questions, and we will see you again at our next live session. Take care, everybody.